Fitting up. Yeah, so hello, I am Swayam Sekhar, and this is our hackathon task is to generate quantum random number, and our group member is Tushar Ambuj, and I am Swayam Sekhar. So basically, our task is to generate a random number, and this is the content. The contents basically the introduction. In introduction, I describe what is classical random number. Then after that, what is quantum random number, and how to generate quantum random number using Qiskit. Then after that, I describe what is noise. Then after that, error mitigation. So first introduction. So what is classical random number generation? So it uses algorithm to generate random number based on the mathematical formulas. So how can we, what is this implies? So basically the classical random number generations are pseudo random number. They are deterministic and can be predicted with sufficient information. Then after that, I come to true randomness and quantum random number generation. So what is the quantum random number generation? Utilizes quantum mechanics where outcomes of the quantum measurements are inherently random to generate true random numbers. It exploits the indeterminacy of the quantum states. So quantum measurement results are not deterministic. It gives rise to true randomness. The example of the quantum randomness, we can describe the quantum randomness by some experiment. So one experiment is the Stan-Gerlach experiment. So what is the Stan-Gerlach experiment? Describe that we have an oven, and in that oven we have a cesium atom. So cesium atom basically heated, and the electron basically travel through the inhomogeneous magnetic field, and we can see that after measurement, we can see that some electron going up, some electron going down, and it is completely random that which electron, we cannot say which electron going up or which electron going down. So by this experiment, we can show that the process is completely random. Then after that, we can basically describe what is the algorithm to generate quantum random number using Qiskit. So basically, this is the algorithm. First, we have to initialize the quantum circuit. Then after that, we apply a header market. Then we measure the qubit. Then we execute this circuit in simulator and both in simulator and in quantum hardware. After that, we collect the result. Then after that, we generate the random. So so basically this is the circuit of this quantum random number generation. What is this circuit tells about? We have five five qubits, and after that we apply Hadamard and measure all the qubit. Then after that we get the collapsed state, and this collapsed state we can convert this. We can get this collapsed state in the binary, and after that we convert into decimal. We get the random number. So after that, uh, what is basically after implementing this circuit, we have saw there are some noise out there. So what is the cause of this noise? Before that, we basically I briefly talk about what is noise. Noise is basically unwanted disturbance that's affecting the qubit. And what is the source of this noise? Basically, uh, 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 it can be from the environmental interference or imperfect fabrication or control errors. And how can we reduce this noise? So basically, there are several methods. One is mitigating noise. Another one is error correction. Then zero noise explore, explore exploration, basically extrapolation, and after that probabilistic error amplification and environmental shielding. So there are several methods to reduce the noise on depending on the what noise are there. So we apply any of this method to reduce the noise. Then after that, this is basically our code. First, we have to install the Qiskit packages. Then we import these packages. Then last, we have to design a circuit that we apply the header mark so that it can get it can implies that all the qubits are in equal superposition state. Then after that we get some result, and this result can be shown in the bar graph notation. So after that we have to generate basically we have to generate quantum random number by this code. And so basically this code, the output of this code, basically the counts, it basically say that means which quantum state we are basically get, and how many times this the final quantum state occurs or get. So basically this is the raw count, and the corrected count will be stored in the this graph. And after that we code for a, PEA mitigation. So it is in previous slide I talked about so many kinds of error mitigation or reduce the noise, the methods of reducing noise. So we use PEA mitigation. So basically this is the code of the PEA mitigation. Then after that, after the mitigating, we get some result. Then after that, this result will be can be shown in the histogram format. So we can see that there are in the previous slide we get some error. Then after that we have normalized count after mitigating this error. So after that we get a readout error correction. It is another kind of error correction. And after that we can apply another kind of error correction, basically ZNA error correction. And after that we can apply this ZNA code. Then we can compare all this error correction. Then we can see that basically noisy hardware, we can get the result of noisy hardware. Then after that we apply PEA mitigation error. Then after that we can get readout mitigation. Then we can get out ZNE mitigation. So I have compared this all this error correction method. Then after that we get all so basically we say basically in previous slide we can see that the most efficient way is basically in our code. The most efficient way is a PEA mitigation, error mitigation. So after that we can get the random numbers. Thank you.